Right, welcome to Basics to Brilliancy B2B. This is season 2 of trigonometry, whereby we unpack your grade 12 material. Specifically, you're joining us for episode 5, whereby we deal with trigonometric equations to determine general solutions. So, without wasting any time, let us get into it. So, firstly, we will discuss just briefly the five-step method that we will use throughout this episode to determine a general solution. So, just assume you are given a trigonometric equation. And then within that trigonometric equation, there is two or more trigonometric ratios. For example, let's say there is sine and there is cos in the same trigonometric equation. Now then, the first step that we are going to perform is to then strive for a single trigonometric ratio. So what does that mean? So remember, we are assuming that we are given a trigonometric equation with two trig ratios, for example, sine and cos. Then what we want to strive for from that trigonometric equation, we must ensure that we only have one trigonometric ratio, either sine or cos or tan. It really doesn't matter, but as long as we have one trigonometric ratio, that is all good and well. So that is the first step of determining a general solution. 4 out of 5 step of the five-step method. Then the question is, how do we then strive for that single trigonometric ratio? So what is written in red, it answers the question of what to do. This is what you are going to do. You are striving for a single trigonometric ratio. Then the second part answers the question of how to do that. How do we strive for a single trigonometric ratio? We will demonstrate obviously throughout this episode, but we will just want to touch briefly now. So you can perhaps use trigonometric identities. For example, if you have sine squared x, you can replace that with 1 minus cos squared x. So those are trigonometric identities. And they were discussed extensively in episode 1, all of the trigonometric identities that we have. So you can catch up on that episode to get a firm understanding of trigonometric identities. Also, we can also use what we refer to as reduction formulae, which are found within the cast diagram. Also, you can catch up on that using episode 1 of this series. Those were discussed extensively in that episode. All right. Now that we have a trigonometric equation that has a single trigonometric ratio, then what do we do? We must then make that specific trigonometric ratio to be a subject of the equation. That is the second step. What do we want to do? We make the trigonometric ratio. If it is sine, we will make sine the subject of the equation. If that trig ratio is cos, we make cos a subject of the equation. That is the purpose. But then the question is, how do we do that? Well, the answer differs from one scenario to another, but perhaps it can include removing brackets. It can also involve collecting like terms. It can also involve factorizing. It can also involve using a quadratic formula. So it really differs from one equation to another. We will obviously demonstrate this throughout the episode. So the second step, what do you do? You make the trigonometric ratio the subject of the equation. How do you do that? You remove brackets, collect like terms, factorize, and so on. You will perform quite a lot of algebra within the second step. So eventually, at the end of the second step, you must have something similar to trigonometric ratio is equal to a constant. The constant can be plus or minus. It really depends on the scenario. It can be positive, it can be negative. It depends from one equation to another. All right, so that is the second step. This is what you do. This is how to do it. And then we move into the second step and into the third step. Now that we have the trigonometric ratio as the subject of the equation, what is next? Then we determine something that we refer to as the reference angle. Very important, determine the reference angle without using the sign of the constant. So this method that we will focus on is without using the sign of the constant. Obviously, there are other methods whereby you can use the sign of the constant and still get the same answer, and then find other ways to then sort of accommodate the fact that we have used the sign of the constant. But for this episode throughout, we stick to one option, which is without using the sign of the constant. Remember, this constant here, we said it can be positive or it can be negative. For example, let's say we have sine 3 theta. Then that sine 3 theta is equal to negative 1 over 2. So sine in this case is the trigonometric ratio, and it is the subject of the equation. And then on the left-hand side, we have our constant, and it is a negative constant. If we want to determine the reference angle, therefore, we will press in our calculator, shift, press sine, and then you substitute half. You leave out that negative. All right. Take that half and substitute within those brackets, press your calculator, you get 30 degrees. And then this is the reference angle. Very important to emphasize, within the general solution, that 30 degrees is not 3 theta. Let me repeat again. That 30 degrees is not equal to 3 theta. So at this stage, which is step 3, don't do the mistake of saying 3 theta is equal to 30 degrees, because you might end up dividing by that 3 now, and that is a very big problem. So at this step, at step 3, we are determining a reference angle. So say reference angle is equal to 30, as opposed to saying 3 theta is equal to 30. Preferable reference angle is equal to 30 degrees. All right. And then now that we have the reference angle, what comes after that? We must then choose the quadrants that we are going to use. Now, in step 3, we said determine the reference angle without using the sign of the constant. And then we use that sign in step 4 to do what? To choose the quadrants using the sign of the constant. So here's an example. Sine 3 theta is equal to negative 1 over 2. So since the half is negative, that means sine is also negative. Then within our Cartesian plane, we discovered previously in episode 1 that sine is negative in the third and in the fourth quadrant. So that is how we choose the quadrant, using the sign of the constant. The constant at this moment, it is negative. It is negative. Therefore, that also means the trigonometric ratio sign is negative. Then previously in episode 1, we discovered that sine is negative in two quadrants, which are the third and the fourth. And those are the quadrants that we are going to then select. All right. And then we go to the last step of the 5-step method. That last step is the end of determining the general solution. That is when now we solve for the angle. You see at step 5, that is when now you can say 3 theta is equal to, no. Specifically in this case, you will not. But that is when you will say this at this point, 3 theta is equal to something. 3 theta is equal to something. You will see what is that something throughout this episode. But what I'm emphasizing at this point is that at step 3, you do not say 3 theta is equal to 30 degrees. No. You say reference angle is equal to 30 degrees. And then only at step 5, you can then say 3 theta is equal to something. All right. Then let us move into the applications of this 5-step method. So this is what we will use throughout this episode. So keep this in mind. Really, really important. Right, let's deal with the first question. Here we are given 1 plus 4 sine squared x minus 5 sine x plus cos 2x is equal to 0, and check at the marks. 7 marks. When you see that 7, you must rejoice and be like, whew, nice. All right, let's come back. Determine the general solution of that. What is the first step? Let us remember that. The first step of the 5-step method. 1. We want to then strive for a single trig ratio. That is what we want to strive for. As it is currently, we have sine, and we have cos, and that is not right. Ideally, let us have a single trigonometric ratio. Then the question is, how do we do that? Remember, when we were introducing the 5-step method, we said you can do so by using trigonometric identities. And this cos 2x is a trigonometric identity, specifically called a double angle. So we must then change that cos and express it in terms of sine. We cannot change this sine x any further. It is at its simplest form. So we must then convert this cos and make it sine. Right. So we will then have 1 plus 4 sine squared x minus 5 sine x plus. What are we going to replace cos 2x with? Remember, we have 3 options there. And we discussed those options extensively in episode 1. So the first one is cos squared x minus sine squared x. That first option, cos squared x minus sine squared x, is not ideal for this equation. Why? So if we take that and substitute here, there's a problem. We are bringing another cos, and we don't want cos in this equation. We only want sine. So we're not going to take that one. So which other one can we then take? There is 2 cos squared x minus 1. And that also is not helping us. Because if we bring that 2 cos squared x minus 1 here in the place of cos 2x, then we are defeating the purpose. We want our trigonometric equation to have a single trigonometric ratio. So then we are left therefore with 1 minus 2 sine squared x. And now we rejoice. Why? Because this one has only sine. So we can then substitute in the place of cos 2x by 1 minus 2 sine squared x, and then say all of this is equal to 0. Right. Looking at the trigonometric equation now, all of the trig ratio that is there is only sine, and we are happy for that. So that means now our trigonometric equation is expressed using a single trigonometric ratio. Then let us move to the second step of our 5-step method. What is that step? We must make the trigonometric ratio here, which is sine in this case, to be a subject of the equation. We must make that trigonometric ratio, which is sine, to become a subject of the equation. Remember, there is a question of what are we going to do? This is what we are going to do. Make sine x to be a subject of the equation. Then there is a sub-question of how are we going to do that? In this case, we will just collect like terms. For example, 4 sine squared x is a like term with minus 2 sine squared x. So if we add those two, then we must get 2 sine squared x. And then minus 5 sine x is alone gumahamba yedwa. So that is minus 5 sine x. And then 1 plus 1, those are like terms. So 1 plus 1 becomes 2. And then this is all equal to 0. So at this stage, it depends on the algebra that you are comfortable with. Either you find factors or you use the quadratic formula. So we can say if you want to use the quadratic formula, A is equal to 2, B is equal to -5, and C is equal to 2. And then we use our quadratic formula. Remember, when we use the quadratic formula, we are not going to say x is equal to. No, don't do that. We are going to say sine x is equal to. Sine x is equal to. We're not going to say x is equal to minus b plus or minus a square root of b squared minus 4ac. B squared minus 4ac. And then we divide all of that by 2a. And then we continue sine x. We then substitute in the place of b, we substitute by minus 5 plus or minus. In the place of b, we substitute by minus 5 minus 4. What is our a? That is 2. And what is our c? Another 2. And then we divide all of this by 2a. What is our a? 2. Right. Then you press all of that in your calculator. You should then get sine of x is equal to 2, or sine of x is equal to half. Right. We have now achieved our objective, which is to make that trigonometric ratio sine of x to be a subject of the equation. Mm, Yes. So now we are going to therefore our third step within the five-step method. What is that third step? It is to then determine what we refer to as the reference angle. Now we want to determine the reference angle. That is step 3. So we have here sine of x is equal to 2. So if we want our reference angle, then we will say reference angle is equal to shift sine -1 and then you substitute 2. And then you press in your calculator, you should then find that you get undefined, which is error. So what does that mean? That means there is no solution for this particular problem. No solution for sine sine x equal to 2. There is no solution. So no solution. Then let us try and see if we can get a reference angle for sine x equal to half. Let us see. A reference angle is equal to shift sine half. And then you press that in your calculator, you must get that the reference angle is equal to 30 degrees. All right. The reference angle is equal to 30 degrees. And then moving along, we will then go to our fourth step. What is our fourth step? We must choose quadrants. How do we then choose quadrants? We look at sine x equal to half, the equation that we are progressing with. Remember, sine x equal to 2 gave us no solution. So we are no longer progressing with sine x equal to 2. Why? Because it gave us no solution. So now we are referring to sine x equal to 1 over 2. So the constant here, which is 1 over 2, is positive. Therefore, that also means sine itself is also positive. And then sine is positive on which quadrants? That is a really, really, really good question. Sine is positive in the first and the second quadrants. Therefore, to continue forward, we will then use the first and the second quadrant. All right. Then moving along, we will then go to our very last step, which is step 5. What do we do there? We then solve, determining our general solution. So we will continue basically to solve what we refer to as sine x equal to half, because that is the solution, that is the equation that has a solution. The other one, sine x equal to 2, gave us no solution. So we'll say sine x is equal to half, where the reference angle is equal to 30 degrees. So we will first look at the first quadrant. Within the first quadrant, we have theta there. We have theta there, and then theta in this case refers to the reference angle. So when we then determine the general solution, we will say x is equal to the reduction formula theta, which is in this case, theta refers to 30 degrees, plus k times 360 degrees. And that is our first solution. Then to get the second solution, we will then go to the second quadrant. We didn't just pick the second quadrant because we like it or we don't like it. We were guided by the selection of the quadrants. So we then use the second quadrant. The reduction formula that we have within the second quadrant is 180 degrees minus theta. And remember what theta is, the reference angle. All right. Then let us solve for our x. X is equal to therefore 180 degrees minus theta, which is 30 degrees, plus k 360 degrees. Then therefore we say x is equal to 180 degrees minus 30 degrees, that is going to be 150 degrees plus k 360 degrees, where k is the element of integers. All right, that was lovely. I really hope that you have enjoyed this demonstration of the five-step method to solve a general solution, to determine a general solution of a trigonometric equation. So just to recap, the first objective is to strive for a single trigonometric ratio. Either you use your trigonometric identities like we did here, or you use your reduction formulae within the cast diagram. The second objective is to make the trigonometric ratio that we achieved in step 1, now make it to be the subject of the equation. How do we do that? Differs from one equation to another. Sometimes you will remove brackets, collect like terms. We collected like terms here. And then after collecting like terms, we had the opportunity to choose whether we factorize or we use a quadratic formula. And then we used our quadratic formula, making this to be a subject of the equation. Then the third step, determine the reference angle without using the sign of the constant. All right. Then for sine x equal to 0, we didn't get a solution. For sine x equal to half, we got the reference angle to be 30 degrees. And then for selecting quadrants, we use the sign of the constant. Sine x equal to half, that is positive. Therefore, sine is positive in the first and the second quadrant. And then we then solve our problem. First quadrant, we have the reduction formula, theta. Not necessarily a reduction formula, but it's an angle between 0 and 90 degrees, theta, in the first quadrant. And then within the second quadrant, we have an angle referred to as 180 degrees minus theta, the reduction formula. And then therefore you substitute your reference angle. You conclude by saying K is the element of integers. All right, that was lovely. You don't necessarily have to write all of these steps in terms of writing the heading, single trigonometric ratio. No, you don't have to write them. I'm just writing them for illustration purposes, just for teaching purposes, so that at the back of your mind, you can reason properly and be like, okay, now what am I doing? I am making a single trigonometric ratio. When you are done, what am I then doing? I am making that trigonometric ratio a subject of the equation. When you are done, what am I then doing? I am determining a reference angle and so on and so on. So these headings are necessary for teaching purposes. I want to groom your reasoning process so that you know now this is what I'm doing. At step 2, this is what I'm doing. At step 3, this is what I'm doing. All right. You have now an opportunity to pause a video and then attempt that given problem. I assume now that you have attempted the video, therefore we can move into the solutions and then compare with what you got. So what we have here is that we have 4 plus 7 cos theta plus cos 2 theta equal to 0. What is the first objective? Strive for a single trigonometric ratio. What do we have here? 4, 7 cos theta plus cos 2 theta equal to 0. That trigonometric equation is in terms of a single trigonometric ratio, which is cos. So the first step is already sorted. We don't have to do anything to make or to strive for a single trigonometric ratio. It's sorted. All right. Then we go to the second objective, which is making that trigonometric ratio that is existing in that equation to be a what? A subject of the equation. But before we do so, we must make sure that these angles are the same. For cos, we have theta on the second term. And on the third term, we have 2 theta, and that is a problem. These are different. We must then make them to be the same. So that means we must then change cos 2 theta into an expression that contains theta. So cos 2 theta is a double angle, and we have many options within that double angle. To be specific, we have 3, and we discussed them previously. So when we select one option to replace cos 2 theta, we must select the one that contains only cos. Why? So that all this trigonometric ratio can remain in terms of one single trigonometric ratio, which is cos in this case. All right. Then from there, you do what you are good at. Collect like terms and. So 2 cos squared theta seems to be a loner. There is no like term for that. 7 cos theta, there is no like term for that. And then 4 minus 1, those are constants, and then you get 3. And then you observe now the steps that you had performed, and then you make that to be the subject of the equation. All right. Then for cos theta minus 3, we are not going to get a reference angle. What does that mean? No solution. For cos theta equal to negative half, the reference angle is 60 degrees. Here is what to note. When we were determining the reference angle using half, we did not bring that negative. So this third step is determine the reference angle without using the sign of the constant. So we left out that negative and then just substituted half. And then we got 60 degrees. Right? Then you choose quadrants. Cos theta equal to negative half is implying that cos is also negative. And that happens on which quadrants? Second and the third quadrants. And then we solve within the second quadrant. What trigonometric ratio do we have? 1/8. What a reduction formula do we have? That is what I meant. Within the second quadrant, what reduction formula do we have? 180 degrees minus x. What is this x? It is the reference angle, which is 60 degrees. So we say theta is equal to 180 degrees minus x. What is x? 60 degrees. And then within the third quadrant, we ask ourselves, what reduction formula do I have? 180 degrees plus x. What is our x? It is the reference angle. And then you have theta is equal to 180 degrees plus 60 degrees plus k times 360 and so on. Then you close by k is the element of integers. And that is how it goes, folks. That is how it goes. Now we will go move along into another question. Right. In this question, we are given sine squared x plus sine 2x minus 3 cos squared x, that being equal to 0. We must then determine the general solution. What is our first step? We see sine, we see cos. That combination is a problem. We have two trigonometric ratios. So we must then strive for a single trig ratio. Right? We must strive for a single trig ratio. All right, let's go. We have sine squared x, we have sine 2x, we have cos 2x. This 2x here is a problem. We must make these angles to be the same. Let's begin there, making the angles to be the same. So how are we going to then change this 2x into x? This therefore is sine 2x, which is a double angle of sine. So how do we then change that? We will keep the sine squared x and then change sine 2x into 2 sine x times cos x minus 3 cos squared x equal to 0. You see, now we have angles that are the same, x, 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 x. But we still have the problem that we were trying to remove, which is we have two trigonometric ratios, sine and cos, and that is a problem. We must then try to remove this problem. How do we do that? Remember, we spoke about factorizing and so on. This is requesting that we factorize for that specific problem. Let us just go back to algebra. How would you deal with a squared plus 2b, 2ab? How would you factorize a squared plus 2ab minus 3b? How would you factorize that? So this would be factorized in this way. We would say this is equal to, we open brackets, we would say a squared, the factors for that are a, and then 3b, the factors for that, 3b squared, yes. 3b squared, the factors for that are 3b and b. So we have a negative here as the sign of the last term. So what does that mean? It means that the signs within these two brackets must be different. So that is what that negative means. The signs within those brackets must be different. That is the first thing that it means. The signs within those brackets must be different. So that is what it means. And then this middle sign here is positive. The sign of the middle term is positive. So what does that even mean? Is that since our signs are different here, then between 3b and b, the bigger one must take the sign of that middle term. Let me repeat. The last term is negative. So what does that mean? The signs within those brackets are different. That is what it means. The sign of 3b and the sign of b must be different. Why? The sign of the last term here is negative. Okay. Then we have a positive here as the sign of the middle term. What does that tell us? It means that as these signs are different here between 3b and b, the bigger one between 3b and b must take the sign of the middle term. So we are then going to have plus here. We're then going to have a negative there. And that, folks, is how we would factorize that in algebra. So now let us come back to the problem that we have at hand. How would we then factorize sine squared x plus 2 sine x cos x minus 3 cos squared x? That is exactly the same as a squared plus 2ab minus 3b squared. In the place of a, we just have sine x. In the place of b, we just have cos x. Otherwise, what we have on our left-hand side is the same as what we have here. So this would then be, we open brackets, we say therefore sine squared x, the factors for sine squared x is sine x. The factors for sine squared x is sine x and sine x. I think I need bigger brackets. So this is going to be, let's extend, I need the bigger space. So sine squared x, the factors for that are sine x and sine x, as we did with a squared. And then the last term is 3 cos squared x. The factors for that would be 3 cos x times cos x. And then the sign that is for the last term is negative. What does that mean? These signs are different. These signs within these brackets are different. But the middle term has a positive sign. So what does that mean? The bigger one between 3 cos x and cos x must take the sign of the middle term. And the middle term is having a sign of plus. And therefore this by default will then become negative. And that, folks, is how you factorize that. It's algebra. So if you're struggling a bit here, then your issue is not necessarily trigonometry, but algebra. But nonetheless, we have not established a single trigonometric ratio. That is what we are still working towards. Then let us continue. We will then now say each of these brackets is equal to 0. We will say sine x plus 3 cos x is equal to 0, or sine x minus cos x is equal to 0. So we make each of those brackets to be equal to 0. We still have a problem. In this equation, we have both sine and cos. Similarly, in this second equation that we have now, we have both sine and cos. So we still have the problem of two trigonometric ratios. But how many trig ratios do we want per equation? Only one. Right. Now let us then continue. We will keep the sine x in the first equation. And then we take the 3 cos x, which is positive on our left-hand side, and then we take it to the other side of the equation. It becomes, therefore, negative cos x. Then we see, we have sine and cos. We have a trigonometric ratio that combines both sine and cos. And that, folks, is tan of x. What is tan of x? Is sine over cos x. So that means at the denominator, we must have what? We must have cosine of x. Then we must divide here by cos of x, and then also divide here by cos of x. And then voila, we see that the cos of x and the cos of x cancel one another. Sine of x over cos of x is then equal to tan of x. Tan of x will be equal to negative 3 because the cos and the cos cancelled one another. And in this first equation, folks, we have arrived or achieved our objective. What was the objective? Strive for a single trigonometric ratio. All right. Then let us move into our second equation, this one. Sine x minus cos x is equal to 0. We will then do a similar thing, take the negative cos x to the right-hand side of the equation. And then we must then divide on both sides by cos x. Why? Because we want to create tan x. We divide here by cos x, and then we divide also there by cos x. And then what do we get? Sine over cos then gives us tan. And then cos over cos, that gives us 1. Not 0, 1. So this is then equal to 1. And that, folks, is the end of our first step, which is to strive for a single trigonometric ratio. Then let us go to our second step. What is that step? The second step is to say, now that within these equations, we have what we refer to as a single trigonometric ratio. Can we then make it to be a subject of the equation? That is our second step. And we are fortunate enough because in our first equation, we already have tan of x as the subject of this equation. In our second equation, we already have the trigonometric ratio as the subject of the equation. So that simply means the second step for this particular problem is not necessary. Why? Because now all of the ratios the equations that we are working are already sorted. So we don't have to do step 2. Then if that is the case, let us then go to step 3. What is step 3? It is determining of the reference angle. What do we have? We have 2 equations. Remember, the first one being tan of x equal to negative 3. Then the reference angle for that will be shift tan, and then we get the inverse of tan. And then we substitute within those brackets by 3. Not by negative 3, but by 3. And then that gives us 71 59 degrees. So that is our first equation. Let us go to our second equation, which is tan of x, which is equal to 1 in this case. What is the reference angle from that? Tan of x equal to 0, equal to 1. Then we will say shift tan, we get inverse of tan, and then we substitute by 1, and then our reference angle is equal to 45 degrees. And that, folks, is how we determine the reference angle. Moving along into our fourth step, which is to then now choose what we refer to as quadrants. We must then choose what we refer to as quadrants. So remember, we have two equations here. The first equation being tan x is equal to -3. So there will be a set of quadrants specifically for this equation. Then the second equation is tan of x equal to 1. Then there is a set of quadrants that we will use specifically for that equation. All right. So what we are then going to say to ourselves is tan of x is equal to -3. Okay. So that means tan is negative. Then tan is negative on which quadrants? On the second and on the fourth quadrants. That is what we studied in episode 1. Tan x on the second equation is positive, which is +1. Then tan is positive on which quadrants? On the first and on the third quadrant. And that is how we select the quadrants that we are going to use. Now that we have selected the quadrants, we must then go to our very last step, and that is step number 5 out of the 5-step method. What is step number 5 about? Step number 5 is about basically solving for what we have always been solving for, which is determining the general solution. We must then solve. So here we have a lot of quadrants to deal with, but we will do them one by one. Let us say we focus first on the equation tan of x is equal to -3. Tan of x is equal to -3. And the reference angle for that, remember, it was 71.59 degrees. Then for that equation, remember we selected the second quadrant as one of the options that we are going to use. And then we will say, okay, in the second quadrant, what reduction formula do we then have? 180 degrees minus theta. What is theta in this case? It is the reference angle. So we have 180 degrees minus theta, where theta is the reference angle. So we will then say x is equal to 180 degrees minus theta. What is theta? 71.59 degrees plus k times. Remember previously we were using, I think, sine if not cos, but then we add the k times 360. In this case, since we are dealing with tan, we will then say k times 180 degrees. That is tan. We will then say, okay, all of this is equal to what? 180 degrees minus 71, comma 57. Is it 57 or 59? I think it's 57. The reference angle here is 71, comma 57. Yes, I think so. If I got it wrong, please forgive me. I'm not ChatGPT. I am a human being. 71, comma 57. And then to say 180 degrees minus 71, comma 57, we're going to get 108 degrees, 108, comma 43 degrees, 108, comma 43 degrees plus K 180 degrees, right? And that is the second quadrant. And then we go to our fourth quadrant. Why fourth quadrant? Remember, for specifically this equation, tan x equal to minus 3, we selected the second and the fourth quadrant. So now we have dealt with the second, therefore, we must then go and deal with the fourth quadrant. All right. Then going to the fourth quadrant, we must then remember the reduction formula that we have within the fourth quadrant, 360 degrees minus theta. In this case, theta is the reference angle, 71,57 degrees. So that will then be x is equal to 360 degrees minus 71,57 degrees plus k times 180 degrees. So to say on your calculator 360 degrees minus 71,57 degrees, we will then get 288,43 degrees plus k times 180 degrees. Why are we using 180? Remember, this is tan. All right. Then we are done with the first equation, tan x equal to negative 3. Let us go to the second one. Tan of x is equal to positive 1. What was the reference angle for that? It was 45 degrees. Then how do we then solve for that? We say, okay, which quadrants did we select? The first. Let us then deal with the first quadrant. What are we going to use in the first quadrant? Just theta. What is theta? The reference angle, which is 45 degrees. Don't get confused now, eh? Theta in this case is no longer 71,57 degrees. It is 45 degrees. Remember, we have moved now into this equation, tan x equal to 1. Therefore, the reference angle of this equation is 45 degrees. And that makes our theta to be 45 degrees. Then we will say, okay, x is equal to, therefore, 45 degrees plus k times 180 degrees. Then we select the last quadrant, which is the third quadrant. What do we say there? We say x is equal to, which reduction formula do we have in the third? 180 degrees plus theta. And then we say 180 degrees. What is our theta? 45 degrees plus k times 180 degrees. And that, folks, is the end of this equation. All right. Lovely stuff. Lovely stuff. And then let us move then into a problem that you will then get an opportunity to attempt for yourself. And then once you have attempted that, we will see a solution and then you compare your workings together with the provided solution. All right, pause the video and then attempt. So I do hope and believe that you have managed to attempt the problem. You see that here we have a problem. We have two trigonometric ratios, sine and cos. So we must then strive for a single trig ratio. Very similar to the previous one. Take one bracket equal to 0. Take another bracket equal to 0. All right. And then you do your manipulation. You take the cos x to the right, it becomes negative. You divide by sine on both sides to create tan. Then it becomes 2 tan x equal to -1. And hooray, we have achieved our first step to determine or to strive for a single trigonometric ratio. On the second equation, we don't have to do any manipulation there. Why? Because this trigonometric equation is already in terms of one single trig ratio, which is sine. And then therefore you can move into your next step, subject of the equation, reference angle, quadrants, and. All right. Let us then move into another problem. Now we unpack these kinds of equations now, or questions. 5.4.1 is something that we are not going to do here in this episode. We have an episode assigned specifically for this objective, which is to simplify these expressions. I can't recall now which episode was specifically assigned for that, but within this series, there is an episode whereby we simplify trigonometric expressions. Perhaps you can go and revise that. So we won't do 5.1, 5.4.1. We will then move into 5.4.2, which requires the knowledge of this episode. Determine the general solution of theta for which this expression will be undefined. Right? For which this expression will be undefined. So what does that mean, undefined? That simply means the denominator there must be equal to 0. The denominator must be equal to 0. So the moment we have 0 at the denominator as the only term, then we know that that expression is undefined. It gives us error, basically. So what is in the denominator here? The first denominator contains cos theta plus sine theta, all multiplied by cos theta minus sine theta. Then the second denominator contains cos theta minus sine theta. So we don't have to worry about the second denominator. Why? Because the contents of the second denominator are contained in the first denominator. So we can just simply take the first denominator and say cos theta plus sine theta times cos theta minus sine theta, and we equate all of that to 0. And then therefore, from there we determine a general solution. It's basically very similar to the previous question. So we just then have to strive for a single trigonometric ratio. How do we then strive for a single trig ratio then? We will then take each bracket and equate it to 0. The first bracket being cos theta plus sine theta equal to 0. That is the first bracket. And then the second bracket is cos theta minus sine theta, and then we equate that to 0. So the reason why we didn't take the second uh, denominator to be equal to 0, it's because we were going to have a duplication here. We're going to have cos theta minus sine theta equal to 0, another cos theta minus sine theta equal to 0. We were going to have a duplication. So now that we have here for the first equation two trigonometric ratios, then we must establish one. It becomes a repetition, this thing. Now we will keep sine on the left-hand side of the equation. And then we will take the cos, which is positive, to the other side of the equation. Then it becomes negative. Then what happens after that? We try to create tan. We have therefore to divide by cos theta, divide by cos theta. Then sine over cos therefore becomes tan theta equal to minus 1. Why minus 1? Because the cos and the cos will cancel one another. All right. And then moving along into the second trigonometric equation, cos theta minus sine theta equal to 0. Then we will keep the negative sign on the left-hand side. And then we will take cos theta to the other side, and then it becomes negative cos theta. Then what must we do? Divide by cos on the right-hand side and also divide on the left-hand side. And then we have minus sine theta over cos theta. Then we get minus tan theta. What is that equal to? It is equal to negative 1 because that cos and that cos cancelled one another, giving us a negative 1. All right. And then that is the conclusion of the first step. To do what? To determine those trigonometric expressions, trigonometric equations in a form of having a single trig ratio. All right. Then let us go to our second step. What is our second step? We must then make the trigonometric ratios that we have to be subjects of the equation. That is the following step now, to be subject of the equation. Remember, it's unnecessary for you to write these headings. I'm just writing them down for teaching purposes, so that at the back of your mind, whenever you have not written these headings, but you know exactly what objective are you trying to achieve. So this is to cultivate that thinking process, right? Within these two equations, we have tan theta equal to minus 1. So this is already sorted. Theta there is the subject of the equation. But in the second one, which is minus tan theta equal to minus theta, minus tan theta equal to minus 1, then tan theta is not a subject of the equation. What is the problem? That negative. So we must then remove that negative, divide by -1 on both sides of the equation or multiply by -1 on both sides of the equation. It's up to you. So eventually we'll get tan theta -1 times -1. That gives us a +1. And then we have within that equation the trigonometric ratio, which is tan, as the subject of the equation. All right. Then let us go to our third step, which is to determine the reference angle. Now we want to determine the reference angle. And remember, we do so without using the sign of the constant. So we have ourselves tan theta, which is equal to -1. A reference angle for that is going to be tan, shift tan, then we get the inverse of tan, and then substitute 1. We leave out that negative, substitute 1. Then we get a reference angle of 45 degrees. Right. Then in the second equation, we have tan theta is equal to 1. And then our reference angle is then going to be shift tan, which is the inverse of tan, and then substitute 1. We have only 1 there. So we will then say this is equal to 45 degrees. Oh, so then the reference angles for these two equations are the same. I knew that already, but I had to do the steps nonetheless so that you can even see for yourself that they are equal. It's really beautiful to discover instead of being told. So if I had told you that the reference angles here will be equal, blah, 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 then you wouldn't learn, but you will just memorize. It's really important to discover. Now you will see that, so tan theta equal to -1 and tan theta equal to 1. Both of those equations have the same reference. Why? Because these constants, as much as they differ, they just differ with the sign. Without the signs, then these constants are the same. Without the signs, it's 1 it's 1 and 1. And that 1 and this 1 are exactly what we substitute here in order to get the reference angle. So we substitute 1, we substitute 1. Then we get 45 and 45. And that is why the reference angles here are equal. Yes, discovery is better than being told that, okay, the reference angles here will be equal. Right. Now let us move into the fourth step, which is to choose now the quadrants. To choose the quadrants that we are going to use. Then the quadrants that we are going to use, we will say for tan theta equal to -1, which quadrants are we going to use? Tan is negative at the second and fourth quadrant. Also, in the second equation, tan theta is equal to 1. Then tan is positive on which quadrants? On the first and the fourth quadrant. No, can't be the fourth. On the first and the third quadrant. That is where tan is positive. Then let us go to our last step, which is step 5, to solve. All right. Now then we are going to say, okay, for the first equation, tan theta equal to -1. Remember, what is our reference angle? Reference angle is equal to 45 degrees. So we'll then say theta is, okay, we will pick the quadrant first. For tan theta equal to -1, we have the second quadrant that we are going to use. And in the second quadrant, we have 180 degrees minus x, where x is the reference angle. And that is in the second quadrant. We will then say theta is equal to 180 degrees minus 45 degrees plus k times 180 degrees. Why 180? Because we are using tan there. And then pressing in your calculator 180 degrees minus 45, that should give you 135 degrees plus k times 180 degrees. And then the second quadrant that we have is then the fourth quadrant. That is where tan is negative. What reduction formula do we have in the fourth quadrant? 360 degrees minus x, where x is the reference angle. Then we'll say theta is equal to 360 degrees minus 45 degrees. 360 degrees minus 45 degrees plus k times 180 degrees. You press that in your calculator, 360 degrees minus 45, that should be 315 degrees plus k times 180 degrees. All right, so that is the first problem, which is tan theta is equal to -1. Now let us go into the second problem, into the second equation. Tan theta is equal to +1. And the reference angle is equal to the previous reference angle, which is equal to 45 degrees. Which quadrants did we select? The first one was part of it. And then in the first quadrant, remember, we just use x. And then we say theta is equal to x. What is x? The reference angle, which is equal to 45 degrees k times 180 degrees. And then the quadrant then that we then selected together with the first quadrant for tan theta equal to 1 was the third quadrant. What reduction formula do we have in the third quadrant? 180 degrees plus x. And what is x? The reference angle. So this will be theta equal to 180 degrees plus 45 degrees plus k times 300 and no, not 300 degrees. This is tan, remember? So for tan, we don't use 360 degrees, rather we use 180 degrees. So 180 degrees plus 45 degrees, that gives us 225 degrees plus k times 180 degrees. And k is the element of integers. All right. And that, folks, is how we determine the general solution of the value of theta for which this expression will be undefined. All right. Then you have yourself a problem to attempt. You don't have to, well, you can for practice purposes, but in this episode, we will not focus on 5.2.1, which is to prove. There is an episode set aside specifically for that, exactly the previous episode. So tune in for that and check how do you prove that. For this episode, we will do specifically for 5.2.2 for which values of x in the interval where x ranges from negative 180 degrees to positive 180 degrees will the identity be undefined. You know how it goes. Denominator equal to what? 0. All right. So do attempt that, pause a video, and then you attempt, and then compare the solution. I do hope and believe that you have taken some time to attempt this problem. So the hint here is that that expression or that identity must be undefined. When does that happen? When the denominator is equal to 0. So specifically, what does that mean? The cosine of x at the denominator must be equal to 0. And then we take the root of determining the general solution. The first step, single trigonometric ratio. So cos x equal to 0, that is already containing a single trigonometric ratio. So that is sorted. And then we move to our second step, subject of the equation. Can we make this trigonometric ratio called cos x a subject of the equation? It is already the subject of the equation. So that is sorted as well. And then the third step, we must determine the reference angle. We then take the inverse of cos and say substitute by 0 and say that is equal to 90 degrees. All right. And then after having determined the reference angle, we then come and choose quadrants. We say, okay, cos x is equal to 0. Well, there is a huge debate of whether 0 is positive or negative. But I think we have bigger problems than that. I mean, there is another debate of whether 0 exists or not. And that is a debate that exists. So if you say 0 exists, for example, then you say, what is 0? 0 is nothing. Then how can nothing exist? So it's a debate that we must not concern ourselves about right at the moment in time. When you leave high school and you come into the institutions of higher learning and join us here, you will then, perhaps if you're enrolled in the faculty of either education or science, and then you continued doing your mathematics, then you can join that debate and the debaters themselves. But for now, let us just assume that 0 is positive. Cos of theta is equal to 0. That means positive. So also cos is positive on which quadrants? First and the fourth quadrant. Right. And then after having selected the quadrants, we can then solve for our general solution. We will then say the first quadrant, we use theta. What is theta? The reference angle. Therefore, x is equal to theta, which is 90 plus k360. Fourth quadrant, what reduction formula do we have? 360 degrees minus theta. Then x is equal to 360 degrees minus theta plus and so on. And then you have your x is equal to 270 degrees plus k times 360 degrees. All right. So if we were determining the general solution, we were then going to stop here. This is the end. However, we want to calculate the actual values of x that belong within that interval. Then we must go to what we refer to as the values of k. Remember, k is the element of integers. So integers are your 0, 1, 2, 3, 4, 5, and so on. Also -1, -2, -3, -4, and so on. So all of those are your integers. To then calculate the actual values of k, we are going to pick a value of, to calculate the actual values of x, we are going to pick the values of k here. For example, if we pick k is equal to 0, and then we substitute in the place of this k, and then press a calculate, we will get 90 degrees. We substitute here by 0, and then press your calculator, you get 90 degrees. And then we ask ourselves, is that x equal to 90 degrees within this given interval? Then yes. So that also means, therefore, that x equal to 0 is part of the values that we have been asked for in 5.2.2. X is one of those values. X is equal to 90 degrees. All right. Now then we change and we go and substitute 1. We substitute there in the place of k by 1. Then we say 90 degrees plus 360 degrees. That gives us 270 degrees. Then we go to the given interval. Is x equal to 270 degrees within that interval? The answer is no. So that means, therefore, x equal to 270 degrees is not an answer for this question. So we are not going to write it down. We're not going to say here x is equal to 270 degrees. Why? Because this value x is equal to 270 degrees is not within that given interval. All right. So if then k equal to 1 fails, if this k equal to 1 fails on the first equation, we don't have to then go for k equal to 2 because it will also fail. Let us then go and check k equal to -1. We will take k equal to -1, this k equal to -1, and then substitute it here. You press a calculator, 90 degrees plus, fully brackets, -1 times 360 degrees. Press a calculator, you get minus 270 degrees. I think so. Yeah, I think so. You get minus 270 degrees. Then we go to the interval once more. Is negative 270 degrees within the given interval? Or within the given domain, to be specific? Within this given interval? Then the answer is no. Minus 270 degrees is not within this domain. So what does that mean then? It means that the -1 is failing for the first equation. Therefore, we don't have to move into k equal to -2. Why? Because -1 has failed. Also, +1 has failed, so we don't have to move to k equal to 2. So then we are done with the first equation. Then we must go to the second equation. When we go to the second equation, we do the same thing again. We begin here at k equal to 0 and say, okay, let us substitute this 0 here. And then you press your calculator, you find out that x is equal to 270, which is not on the interval. And then you go up, go to 1. You take that k equal to 1 and substitute here. You get something even greater than 270, which implies now that 1 has failed for this equation. We don't have to go up, therefore, to k equal to 2. So let us then go to -1. Take your k equal to -1 and substitute right there. And then you press your calculator, you'll get that x is equal to -90 degrees, which is this one. You ask yourself, Is that x equal to minus 90 degrees part of that interval? If yes, which is in this case, it is yes, then you write down x is equal to 90 degrees. And then you change, you go to x is equal to -2. Take that -2, substitute in the place of k, you press your calculator, whatever value that you get, you come and check here. Is it within this interval? You will find out that no, the value that you will get when you use k equal to -2 is not in the interval. Therefore, you don't have to go to k equal to -3, which means the values that we get here are, yes, 90 degrees and -90 degrees. And that, folks, is how we solve this specific problem, which is for which values of x in that given interval will the identity be undefined, right? And then that begins with letting the denominator to be equal to 0. Let us move along into the next set of problems. All right, before we even begin, then the next set, the set of the next problems, before we even begin that, let us just briefly unpack this method, the conversion method. Here we will use things like 90 degrees minus x and 90 degrees plus x. So we use that in equations like sine of theta plus 30 degrees, that being equal to cos of 3 theta. Within that equation, there is sine and cos, which means there are two trigonometric ratios. Then the question is, how do we then strive here for a single trigonometric ratio? Moving into the second example, we have cos 20 degrees minus theta is equal to sine 2 theta. Cos of 20 degrees minus theta is equal to sine 2 theta. There are two trigonometric ratios here. Then the question is, how do we strive for a single trig ratio here? In the second example, in the third example, there is cos 45 degrees plus 2 theta equal to minus sine of theta. How do we then strive here for a single trigonometric ratio? In the last example, there is sine 3 theta equal to minus cos of theta minus 10 degrees. The question remains the same. How do we then strive for a single trigonometric ratio? So, folks, allow me to introduce to you this method called conversion method. Well, I named it myself, so don't go and Google conversion method. Chances are you won't find anything similar to this. So this is not an official name. I've just named it by myself for understanding. We will use what we refer to as 90 degrees minus x, 90 degrees plus x to convert here. What are we converting? For example, in the first example, we want to convert either sine to cos or cos to sine. In the second example, we want to convert cos to sine or sine to cos. In the third example, we want to convert cos to sine or sine to cos. Similarly, in example 4, we want to convert sine to cos or cos to sine. And in episode 1, previously, we saw that 90 degrees minus x and 90 degrees plus x, when we use one of those two in cos, cos must change to sine. If we use one of those two in sine, sine must change to cos. So there is always that effect of conversion when we use 90 degrees minus x and 90 degrees plus x. So that is why, therefore, to answer the first step of a single trigonometric ratio, we will use either 90 degrees minus x or 90 degrees plus x, depending on the scenario. All right. So the question is always, do we convert cos to sine or do we convert sine to cos? Actually, it really doesn't matter. It really doesn't matter. But I would recommend that you check a simpler angle between these two angles. In this case, 3x seems to be a simpler angle compared to a plus, compared to theta plus 30 degrees. 3 theta seems to be a bit simpler than the second angle. Then that means, based on my recommendation, let us therefore convert cos into sine. Right, okay, let's begin then. Let us then begin. When we begin, we will first speak of what was cos of 3 theta before. Before it was 3 theta, what was it before? It was sine 90 degrees minus 3 theta. Oh, what is that now? I know that is what you are saying. But nonetheless, let us walk through it. Let us just say we were given this. What would this become? We would say 90 degrees minus theta is the first quadrant. And sine in the first quadrant is positive. So we would then have positive. And we have sine and cos. We have sine and 90 degrees. What does that mean? We must then convert this sine into cos. So that is what I mean when I say cos 3 theta. Before it was cos 3 theta, it was what? It was sine 90 degrees minus 3 theta. Right. So that is what we imply by the conversion. We have converted now cosine into sine using what? 90 degrees minus x. So cos of 3 theta is therefore equal to sine 90 degrees minus 3 theta. So we can then go to our equation and say, okay, in order to strive for a single trig ratio, we will say sine theta plus 30 degrees, all of this. It was previously equal to cos 3 theta. But we have discovered now that, actually, cos 3 theta is also equal to sine 90 degrees minus 3 theta. Sine 90 degrees minus 3 theta. And that, folks, is how we achieve the first step of our five-step method. We have now our trigonometric equation in terms of sine and only sine. So a question of where to from here. Don't worry about that. That is a debate for the next slide. For now, understand how to convert sine to cos or cos to sine. How to basically achieve the first step, a step of a single trigonometric ratio. Then from there, we speak about where to from here. But understand this step first of all. All right. Let us go into the second example. We say here, okay, we have 20 degrees minus theta and also 2 theta. Which one is simpler than the other between these two angles? We see that 2 theta seems a bit simpler than 20 degrees minus theta. So that means based on my recommendation, let us convert therefore sine 2 theta. Okay. If we want to convert sine 2 theta based on either 90 degrees minus x or 90 degrees plus x, we must ask ourselves a question. Before 2 theta, before sine 2 theta became sine 2 theta, what was it? It was then cos of what? 90 degrees minus 2 theta. Oh, what do we mean now? Okay, wait a minute. Look at this quadrant. 90 degrees minus 2 theta, that is the first quadrant. Then cos in the first quadrant is positive. Therefore, we have a positive there. And then since we have cos and 90 degrees, what will become of this cos? It will become sine. Sine of what? Sine of 2 theta. So that is how we basically convert. Since it's sine here, we have cos here. Since it is 2 theta here, we have 90 minus 2 theta there. And then to then achieve a single trigonometric ratio, we'll say, okay, cos 20 degrees minus theta. Initially, it was equal to sine 2 theta. Now we have discovered that actually sine 2 theta is equal to cos 90 degrees minus 2 theta. Therefore, we are going to replace that sine 2 theta by cos 90 degrees minus 2 theta. And voila, our trigonometric equation now is in terms of a single trigonometric ratio. I know you have a question of where to from here. I understand, but hold your horses. Just understand this for now. A question of where to from here, it's a question for the later stage. Just understand this conversion first. All right, let us move into the third, and the fourth problem. We have 45 degrees plus 2 theta as the first angle, and then our second angle is theta. Then the question is between the two, which one is simple? I think you can see it is just theta. Then based on my recommendation, preferable you change minus sine of theta. All right, let's go back to our question. Before minus sine theta was minus sine theta, what was it? It was cos 90 degrees. Not minus now, but 90 plus. Wow. How? Hold on. So we have 90 degrees plus theta. Which quadrant is that? A second quadrant. Okay. So what is the sign of cos in the second quadrant? Yes. Sign of cos in the second quadrant is negative. So that is why we have picked this one that says 90 degrees plus. Why? Because there is this negative that we want to accommodate. The negative, that is the coefficient of sine. So now you get the ability to differentiate when do I use 90 degrees minus x and when do I use 90 degrees plus x. When your coefficient for sine and cos is positive, it doesn't matter which one you use between those two. 90 degrees minus x, 90 degrees plus x. But so far we have used only 90 degrees minus x. So you can just stick to that. It really, doesn't matter. You can stick to 90 degrees minus x. When the coefficient of x, of sine and cos are positive, right? But when the coefficient specifically for sine is -1, then that calls for 90 degrees plus x and only 90 degrees plus x. So keep that in mind. When the coefficient of sine is a -1, that calls for this one, specifically that one. Otherwise, when the coefficient of cos and sine are +1, it really does not matter. Whether you use the 90 minus or 90 plus, you get the same answer. But when the coefficient of sine is negative, use exactly 90 degrees plus. All right. Let us then write it as a solution for the single trigonometric ratio. We will then say, okay, cos 45 degrees plus 2 theta is equal to. Initially, it was -2. It was negative. It was equal to negative sine theta. But now we have realized that negative sine theta is equal to cos of 90 degrees plus theta. Cos of 90 degrees plus theta. All right, that is how we achieve the same or a single trigonometric ratio. Yes, you have a question of where to from here. Don't worry. So let us move into example 4 as a last example that we will use for demonstration. Be careful when it comes to example 4. You see now we have this negative, but this negative now is a coefficient of cos. So preferable, you take that negative to the left-hand side. Preferable, our negative coefficient must be with sine, not cos, preferable. All right? So we will then take this negative to the other side of the equation, and then we will have negative sine 3 theta is equal to cos of theta minus 10 degrees. So there is something now that you are discovering here. Preferable, the coefficient of cos is +1, always preferable. The coefficient of cos is always +1 in order for you to apply this conversion method. However, the coefficient of sine can either be +1 or -1. It doesn't matter. We saw in the second problem, in the second example, the coefficient of sine there was positive. And the coefficient of sine in the third problem was negative. We were able to still convert. So that was not a problem. It's a problem though if the coefficient of cosine is -1. You must take that negative to the other side of the equation. And then you have the -1 as a coefficient of sine. And then the coefficient of cos remains as +1. And then from there, we can just convert this left-hand side. We see that we have the negative sine of 3 theta. Then we go back to our question. Before, negative sine 3 theta was negative sine 3 theta. What was it? It was cos 90, wait for it, plus 3 theta. So let us revise. Whenever our sign has a negative coefficient, -1, we always use to convert 90 degrees plus, 90 degrees plus. Always, folks, always. Why? Because this goes to that thing of which quadrant is indicated or represented by 90 degrees plus 3 theta. That is the second quadrant. And in the second quadrant, what is the sign of cos? Negative. Therefore, that is where this negative comes from. All right. And then with that being said, we can then replace the left-hand side of this equation by cos 90 degrees plus 3 theta. Cos of 90 degrees plus 3 theta, all equal to cos theta minus 10 degrees. All right. And folks, that is how we strive for a single trigonometric ratio in equations like this. We did quite a lot. Example 1, example 2, example 3, example 4. I won't lie, I really tried to explain. Let us sort of make a summary or things that you must note. Note that I think I have mentioned that the first one is that the coefficient of cosine must always be +1. So that is the coefficient of cosine must always be 1. So you saw that then the coefficient of cosine was +1. You saw here in example 2, the coefficient of cosine was +1. You saw there in example 3, the coefficient of x was +1. You saw in example 4 that the coefficient of x was -1. But we then multiplied on both sides of the equation by -1 to remove this negative, so that our coefficient of x is there, of course, is then +1. So keep that in mind. Really important to note. And then the second thing to note is that the coefficient of sine now. What about it? It can either be +1 or -1. The coefficient of sine can either be positive or -1. It really doesn't matter. Let us go to our first example. The coefficient of sine there was +1. The coefficient of sine here was +1, and we used 90 minus. The coefficient of sine here was negative. The coefficient of sine here was negative. So the difference here is that when the coefficient of sine is +1, we can either use 90 minus or 90 plus to convert that sign. When the coefficient of sine, not the coefficient of cos, no, no, no. The coefficient of sine here is +1. We can then either use 90 minus or 90 plus to convert that sign. However, when the coefficient of sine is -1, then we can't use 90 minus x. We must use 90 plus. Right, I think that is enough to to introduce you in this conversion method. Let us then go to an example. Now, within this example, we will even go beyond now just the explanation of striving for a single trigonometric ratio. We will even answer the question of where to from here. Let us then strive here for a single trig ratio, right? Let us strive for a single trig ratio. We have sine x plus 30 degrees equal to cos 3x. I think you can tell that x plus 30 degrees is a bit more complicated than x than 3x. So we can then take 3x to convert. We can take, cos x to convert. So what was cos 3x? What was cos of 3x before it was cos 3x? Using either 90 degrees minus or 90 degrees plus. Then we will say this was sine of 90 degrees minus 3x, right? Then to strive for a single trig ratio, we will say sine is equal to x plus 30 degrees equal to, initially it was equal to cos 3x, but we have converted that and expressing it in terms of sine. 90 degrees minus 3x. Right. And then from there, we see that there is sine and there is sine, which means now our equation is in terms of a single trigonometric ratio. And that, folks, then leads us to the second question that the question that you have always been asking yourself, a question of where to from here. So we will then go to our second step, whereby we then express that trigonometric expression as the subject of the equation. And that is already sorted in the equation that we are working with. Sine here on the left-hand side is the subject of the equation. Sine there on the right-hand side is the subject of the equation. So this is sorted. We don't have to bother ourselves regarding that step. And then we will go to the third step. What is the third step? We want to determine our reference angle. Reference angle. And in order for us to determine our reference angle, we go back to our equation. We have sine x plus 30 degrees equal to sine 90 degrees minus 3x. So when it comes to determining the reference angle, you basically pick any of these two, either x plus 30 degrees or 90 degrees minus 3x. You pick any of them and you make it a reference angle. So you just pick any. It's your choice. But remember your choice. Pick any. So our reference angle, for example, in this case, we can say it is equal to 90 degrees minus 3x. We pick any between those two and make it a reference angle. And then we go to our fourth step, whereby we then now choose quadrants. So for this kind of equations, we choose where the trigonometric ratio is positive, always. We choose for this kind of equations. we choose where the trigonometric ratio is positive. In this case, the trig ratio is sine. So trig ratio sine is positive in the first quadrant and also in the second quadrant. And folks, that is how we do step 1, step 2, step 3, and step 4. And then we will go to our very last step, which is step 5, to solve, therefore, for our angle. So when we solve, we will say, okay, we selected the first quadrant. And then our first quadrant would be represented basically by what we refer to as theta. By now, I think you know what theta is. It is that reference angle, 90 degrees minus 3x. So since we have picked 90 degrees minus theta, remember I said when you pick any angle between the two, you must pick any, but remember your choice. So we have picked 90 degrees minus 3x as a reference angle. So now when we solve, therefore, we will go and take x plus 30 degrees and then say x plus 30 degrees is therefore equal to, right? Then we'll then say x plus 30 degrees is equal to theta. What is theta? Our reference angle. 90 degrees minus 3x plus k times 360 degrees. Then we collect like terms. The negative 3x on the right hand side will come to the left hand side and give us a positive 3x. The 30 degrees on the left hand side will come to the right hand side and become negative 30 degrees. Now x plus 3x, that becomes 3x equal to 90 minus 30 degrees, that gives us 60 degrees plus k times 360 degrees. Then we divide 4 on both sides of the equation. 60 divided by 4, that gives us 15 degrees times 360 degrees divided by 4, that gives us 90 degrees. Right. Then we go to our second quadrant. And remember, within the second quadrant, we have reduction formula of 180 degrees minus theta. What is theta? The reference angle, which is 90 degrees minus 3x. All right. Then we will say once more, x plus 30 degrees. Where does that come from? The angle that we did not pick as a reference angle. That is the angle that we're going to place over there. The angle that we did not pick as a reference angle. 180 degrees minus, what is theta, which is the reference angle? 90 degrees minus 3x plus k times 360 degrees. Now we will say, okay, x plus 30 degrees is equal to 180 degrees minus 90 degrees. Minus times a minus, that should give me a plus k 360 degrees. Then we say, okay, x plus 30 degrees. 180 degrees minus 90 degrees, that is 90 degrees plus 3x plus k times 360 degrees. And then we collect like terms. The 3x on the right-hand side comes to the left-hand side and becomes negative 3x. The 30 degrees on the left-hand side of the equation come to the right-hand side of the equation and becomes negative 30 degrees plus k times 360 degrees. X minus 3x, that is minus 2x, 90 degrees minus 30, that is 60 degrees plus k times 360 degrees. All right. Then we divide on both sides of the equation by negative 2. 60 divided by negative 2, that is negative 30 degrees. And then k times 360 divided by negative 2, 360 is going to be 180 degrees. So here now it doesn't matter whether you say minus or you say plus, it really doesn't matter. Why? Because k is the element of integers. And integers can be positive 1, negative 1, it really doesn't matter. So here it's your choice as to which sign do you substitute. You can even keep it as negative. It's up to you. All right. And folks, that is how we deal with this kind of equations, determining the general solution. Nice, lovely, lovely. Without wasting any time admiring this problem, let us move into the next one. Before we go to the next problem, let me introduce another method for achieving the first step, which is the single trigonometric ratio step. How do we achieve that? So in this question now, we have root of 2 times sine theta is equal to cos of 45 degrees minus theta. There is a problem here, which does not allow us to use the conversion method. The method that I'm introducing now is called the expansion method. We expand using compound angle identities. That is when we cannot apply the conversion method. So here we cannot apply the conversion method, and only because of this guy. Remember, what did we say previously? What must be the coefficient of cos? We said it must strictly be positive 1. And it is in this case. We are happy with that. What did we say about the coefficient of sine? We said it can either be positive 1 or be negative 1, between those two, but not anything else, not a root of 2, not a 4. It can strictly be either positive 1 or negative 1. So in this question, you might be tempted to convert, but no, you can't, not yet. So in this case, therefore, what can we do? We then apply what we refer to as the expansion method. So how does it work? We say, okay, we keep the root of 2 sine theta equal to cos of 45 degrees minus theta. Let us make it cos of 45 degrees plus theta, just for interest's sake. You can still apply it even if it's minus theta, but I'm just more interested. There's something that I want to demonstrate, which I cannot demonstrate if it was minus. So what are we then going to do here? We're going to expand. This is a compound angle. So this is going to be cos of 45 degrees, cos of 45 degrees, cos of theta. Since we have positive here, it must then be negative here. Then it becomes sine of 45 degrees times sine of theta. So we expand now that cos using what we refer to as the compound angle identity. If it was sine here, we were going to do the same thing. Expand that using the compound angle identity of sine. Right? And then now we say root of 2. Remember, we want to strive for a single trigonometric ratio. At the moment, we still have sine, we have cos, and then we say sine theta equal to cos of 45 degrees is your root 2 over 2. And then sine of 45 degrees is your root 2 over 2. That is a special angle. Sine of theta. And now this stage that we are at now, the fact that we were able to press within our calculators for sine 45 degrees. So that means preferable when we are doing this problem, this numerical angle here, preferable, it should be a spatial angle. Because imagine that 45 degrees was 40 degrees. Let's say it was 40 degrees here. Where were we going to get the value for cos 40 degrees? So I'm not saying it is not solvable if it is not a spatial angle. Obviously, it is still solvable. But for easy calculations, I think you would appreciate for that angle to be a spatial angle. Right? And then we then going to collect like terms. You see that sine is on the left hand side. So let us take everything that involves a sine on the right hand side and bring it to the left hand side. Minus root 2 over 2, actually plus sine theta equal to root 2 over 2 cosine of theta. So now what we have done is collecting like terms. Also, that brings us to the next important point. The first important point was that we were able to press sine 45 degrees in a calculator and we got root 2 over 2, which meant that preferable the numerical angle, which is the angle that is a number like 45 degrees, then preferable the numerical angle is a spatial angle, preferable, because it is going to make your life easy when it comes to the calculations. And then going to the second important point now, what we have just discovered is that this sine root 2 of sine theta and that negative root 2 over 2 times sine of theta, those two are like terms. What makes them to be like terms is that the angle of sine here is theta and the angle of sine there is also theta. Where does that come from? Even at the beginning, we had theta there and we had theta there as well. So this then leads us to the second important thing within this method. The variable angles must be the variable angles must be the same. Preferable, the variable angles are the same. So what do I mean? So in the previous, at the beginning of this problem, on the left-hand side, the angle was theta. On the right-hand side, the angle was 45 degrees plus theta. So that 45 degrees is what we refer to as the numerical angle. Then theta and theta are what we refer to as the variable angles. So the numerical angle, preferable, it must be a special angle. Then the variable angles like theta and theta, they must be the same. How can they be different? If this is 2 theta and then that one is theta, then these two are different. And that's a problem for this expansion method. If that angle there is not 45 degrees, it is 10 degrees, that is a problem for this specific method, right? So those are the things that you have to note specifically for this problem, that the variable angles must be the same. If we have 45 degrees plus theta, then 45 degrees is what we refer to as the numerical, there is I there. This is what we refer to as the numerical, a number, numerical angle. And then theta is what we refer to as the variable angle. It's a variable, all right? So what do I say? The variable angles must be the same. There is theta here as a variable angle. There is theta there as a variable angle. There is 45 here as a numerical angle, which is a special angle. So these variable angles are the same, and this numerical angle is the same. Then that validates that we can therefore apply this expansion method. If these variable angles are not the same, then it will be quite difficult to work around with the expansion method. If this special angle is not, if this numerical angle is not a special angle, then that leads to a bit of complication. All right. Now let us move along. I just wanted to highlight those two things. So these are things to note. Then here we can collect the like terms. We add root 2 together with root 2 over 2. We should get, what should we get? We should get 3 root 2 over 2 if we add those two in our calculators. Root 3, we should root 2 plus root 2 over 2, that is 3 root 2 over 2 times sine of theta equal to root 2 over 2 times cos of theta. And I think you are familiar with something of that nature. This is 3 root 2 over 2. Now we have sine and cos here. So how can we then combine sine and cos to form a single-digit ratio? Yes, we must divide on the right-hand side by theta. No, by cosine of theta. And then also divide on the left-hand side by cosine of theta. On the right-hand side, cos and cos will cancel one another. And then we will have 3 root 2 over 2 sine over cos, that is tan theta. All of that is equal to root 2 over 2. And voila! We have achieved a single trigonometric ratio. And that is what we were working towards specifically in this problem to illustrate how do we then apply the expansion method? Because we wouldn't be able to convert here sine to cos because the coefficient of sine is not positive 1. Also, it is not negative 1. It is root of 2. And that's a problem for the conversion method. However, we can therefore use the expansion method, which works quite well when the variable angles are the same and also the numerical angle is a special angle. All right, let us then apply this method in the upcoming problem. Here we are given sine of x plus 60 degrees plus 2 cos of x to be equal to 0. Then what can we do? We see that, first of all, can we convert here? Can we apply the conversion method to convert perhaps cos to sine or sine to cos? No. Why? Because the coefficient of cosine is not positive 1. It's not even negative 1 in this case. It is 2. And that's a big problem. So let us then explore the expansion method. Why will the expansion method work now? Because this x and that x, they are variable angles and they are the same. What about this numerical angle? 60 degrees. What is 60 degrees? It is a special angle. So then, in order for us to strive for a single trig ratio, we must then not convert but rather expand. Expansion method using what? Using the compound angle of sine. So that will be sine of x cos of 60. It's a plus, so it remains as a plus even here. Then it becomes cos of x, then sine of 60. Right? Then we say plus 2 cosine of x, all equal to 0. And then we have a special angle. Remember, cos of 60, you can press that in your calculator, then you should get 1 over 2 times sine of x. You press sine of 60 in your calculator, you should get root 3 over 2 times cos of x plus the 2 cosine of x that was already there in the equation. What are we going to do then now is to collect like terms. There is cos, and then we collect like terms. What makes these to be like terms? Just besides the fact that there is cos and cos, the variable angles are the same. So that is why there is a condition for the expansion method, for the variable angles to be the same, because we want to have like terms. That's why. Then we can combine these two. We will say 1 over 2 sine of x, root 3 over 2 plus 2. That will give us root 3 plus 4 all over 2. We multiply then that by cosine of x. Then we can take cos and divide throughout. Divide on our first term by cos, divide on our second term by cos, divide on the right-hand side by cos. What are we going to then get? We will get 1 over 2 sine of x all over cos of x plus root 3 plus 4 all over 2 times cosine of x all over cosine of x is equal to 0 all over cosine of x. Why are we dividing by cosine of x now? It is because we want to establish tan here. So with that being said, we will then have 1 over 2 sine x over cos x, that is tan of x, plus root 3 plus 4 all over 2. What is happening here? Cos and cos will cancel one another. Then what are we left with, therefore? On the right-hand side, we're left with 0 over cos, which is 0. And that, folks, is that trigonometric equation expressed in a single trigonometric ratio, which is tan x. And that is what we have been working for. Right. Now, let us move into our second step, which is to then make that tan x to be the subject of the equation. The subject of the equation. How do we do that? Very simple. We will keep 1 over tan x on our left-hand side. Then we take the root 3 plus 4 over 2 to the right-hand side of the equation. And then it becomes negative there. And then we divide all of that by 2. Tan is still not a subject of the equation. We must then remove this 1 over 2, or that 2 as a denominator. How? By multiplying on both sides of this equation by 2. If we multiply by 2, here we're going to get 2 times half tan, and then say negative root 3 plus 4 all over 2, multiply that by 2. Then this 2 and that 2 will cancel one another, and then we will be left strictly with tan of x. And then on the right-hand side, those 2 will cancel one another, and then we'll be left with negative root of 3 plus 4. All right, and that is, folks, how we make tan of x to be the subject of the equation. Let us then move into our third step, which is to determine the reference angle. Very easy from this point onwards. What is our reference angle? It will be the inverse of tan, which is shift tan, then we get the inverse. We substitute the constant. The constant in this case is negative root 3 plus 4. We will then take root 3 plus 4 and leave out that negative. And then we must get 80,1 degrees as the reference angle. Right. Then after having performed our third step, we go to our fourth step, which is to choose quadrants. We then now choose our quadrants. Very easy. We come to this tan x equal to negative into root 3 plus 4, we see that is negative. And tan is negative on which quadrants? That is your second quadrant and your fourth quadrant. So we are solving here for this equation. Tan of x is equal to negative root 3 plus 4. Tan x is equal to negative all into root 3 plus 4. And our reference angle, as we have seen previously, it is equal to 80 over 1 degrees. Then let us go to the last step, which is to solve now. To solve, all right. Actually, I should have written that one here. Tan of x is equal to negative root 3 plus 4. And then our reference angle is equal to 80, 1 degrees. I should have written that under step 5, which is to solve for our general solution. So now we have to pick those quadrants. The second quadrant is one of the quadrants that we have picked. And in the second quadrant, we have the reduction formula called 180 degrees minus theta, where theta is our reference angle. So that will be x is equal to 180 degrees minus theta, which is our reference angle, which is 80, 1 degrees plus k times 180 degrees. Why 180? Because we are using tan here. X is equal to, therefore, press 180 degrees minus 80, 9 degrees. That should 80, 1 degrees. That should give you 99, 9 degrees plus k times 180 degrees. Then we go to another quadrant, which is the fourth quadrant, where our reduction formula is 360 degrees minus theta, and we know what theta is, the reference angle. Therefore, we have x is equal to 360 degrees minus 80, 1 degrees plus k times 180 degrees. Then x is equal to 279 degrees, 279,9 degrees plus k times 180 degrees. Then k is the element of integers. Right. I do strongly believe that steps like step number 5, it has been a repetition now. At least you are a bit comfortable with that. So that is why I was a bit fast in step number 5. In step number 4, choosing quadrants, I think it's something that you are quite familiar with now. And step number 3, same as well, determining the reference angle. There should be no shock there. Step number 2, making that tan theta subject of the equation. Nothing biggie as well there. Something that might be a bit challenging for you would be step 1, but we dealt with that quite extensively in the previous slide. So if it's a shock, perhaps it's because you're hearing for the first time. Go through it over and over and over again just to make sure that you understand how it goes. All right, with that being said, let us go to our 2 last questions, which are some of the really interesting questions within the general solution questions. And here now we have our trigonometric ratio as exponents. That is why this question is a bit interesting, right? Our very first objective is to obviously strive for a single trig ratio. That is what we fight for. But by the looks of things, it seems like our trigonometric equation is already in terms of sine. So that is sorted. No worries. That is sorted. Then what is our next step? It is to take that trigonometric ratio sine and make it to be the subject of the equation. In this case now, since we have exponents, then to make that trigonometric ratio to be a sine, to be a subject of the equation, then we will include on our steps laws of exponents. Laws of exponents. So let us just discuss briefly what is that? What are the laws of exponents? Remember in algebra, we said that in algebra, a to the power x plus y is equal to a. We distribute a, the base, to each of those exponents. A to the power x times a to the power y. So we distribute that base among those exponents. So in the equation that we have here, we have 10 to the power sine of x plus 1. How can we then deal with that? It will be a to the power, no, not a, 10. The base is 10 now. The base is 10. It will be 10 to the power sine x times 10 to the power 1. So that is one of the exponent laws that we will apply in this problem. So let us then apply it. It will be 10 to the power sine x plus 10 to the power sine x times 10 to the power 1, all equal to 110 degrees. Then what do we see now? We see that 10 to the power sine x and 10 to the power sine x is actually a common factor. So we will factor that and say 10 to the power sine x. When we take the 10 to the power sine x, we are left with 1 plus. When we take this second 10 to the power sine x, we are left with 10. All of this equal to 110. Then we say, okay, 10 to the power sine x times 1 plus 10, that is 11, equal to 110. And then we divide on both sides by 11. So we have ourselves 10 to the power sine x equal to 110 all over 11. And that gives us so we multiply, yes, that gives us 10 sine x equal to 110 over 11. That gives us 10. Remember, the exponent of any base can be named to be 1 if it is not written. Right. Remember, in algebra, we will always go back to algebra. If we have 2 to the power y equal to 2 to the power 3, then we can make a conclusion that y is equal to 3. Why? When the bases are the same, we equate the exponents. We have a similar case here. 10 and 10 are the same bases. then we must therefore equate the exponents. Sine of x is equal to 1. And that, folks, is us achieving that objective, making the trigonometric ratio sine to be the subject of the equation. And then from there, we move into the third step, which is determining the reference angle. In this case, our reference angle will be shift sine, the inverse of sine, and then substitute 1, and then we get 90 degrees. Right? And that is how it goes. And then we go to our fourth step, which is to select quadrants now. We select quadrants. And we see that, oh, okay, we have sine of x equal to 1. That 1 is positive. So that means also sine is positive, which is in the first and in the second quadrant. After having selected now the quadrants, we can then solve. Right? What are we solving for? We're solving for theta in the equation that is given to be sine of x equal to 1, where the reference angle is equal to 90 degrees. So that is what we are solving for the value of x in that equation. Sine of x is equal to 1, and then our reference angle is equal to 90 degrees. All right. So the angle, the quadrant that we have selected, the first one is the first quadrant. You know how it goes. The reference angle, which is theta, is 90 degrees. Yes, it's 90 degrees. Therefore, in the first quadrant, we will have x is equal to 90 degrees plus k times 360 degrees. Very simple. I do believe you are comfortable with step 5, step 4, step 3. You might have struggled a bit with step 2. But when it comes to 3, 4, 5, sweet word. Then going to the second quadrant, which is quadrant 2, where we have the reduction formula 180 degrees minus theta, where theta is our reference angle, which is 90 degrees. Then x is equal to 180 degrees minus 90 degrees plus k times 360 degrees. Then x is equal to 180 minus 90 degrees, that is 90 degrees plus k times 360 degrees. So we get the same equation. Nice. All right. We have not answered the question fully yet, for we are given that specific interval there. So this question is very similar to the question whereby we had to then look at the values of k. Values of k. And you know the values of k, which is the integers that exist on a number line. 0, 1, 2, 3, and so on. -1, -2, -3, and so on. So these are the values of k. And then we will, since we have one equation of the general solution here, which is x equal to 90 degrees plus k times 360. So we will use only that equation. since this is the only equation that we have for the general solution. So we will then exchange the values of k just as we did previously. And then we see what values do we get. I got x is equal to 90 degrees and x is equal to negative 270 degrees. I do believe that you are able to get those values and check if they are within that specific interval. All right. So just to recap, I think the new thing here is just the use of the laws of exponents. Everything else is the same. So it's important to always go back to your algebra. You can distribute the base among those exponents. A to the power x plus y is a to the power x times a to the power y. Right? Then you apply that here to split this 10 to the power sine x plus 1. It becomes 10 to the power sine x times 10. Where is that 1 now? That 1 is this exponent, but we don't have to write it. All right, then let us go to our very, very last question in this episode. I know it has been quite a longish episode, so I do believe that during the course of it, while you are watching it, you took some break and you took a snack or something like that. All right. Let us then look into this question. So the first step, as you know, we are trying to express all of this in a single trig ratio. Right? And by the looks of things, the single trigonometric ratio step is sorted here. We see that all of the whole equation here is in terms of time. So we don't have an issue with the trigonometric ratio. Then let us go therefore into our second step, which is express that trigonometric ratio, which is tan, as the subject of the equation. So that is what we want to achieve now. Again, how are we going to achieve that? Since our trig ratio is an exponent, we will include laws of exponent, right? And one of those laws is a law that we have just briefly discussed previously. We said if a to the power x plus y, then that can be distributed into a times into a to the power x times a to the power y. So similarly, therefore, we're going to say 3 to the power tan x plus 1 can be equal to 3 to the power tan of x times 3 to the power 1. We don't have to write that one. It's not necessary. So that is how we deal with the second term, laws of exponents. And then we go to our first term. There we have 3 to the power 2 times tan of x. So if we had, for example, a to the power 2 times y, that could have been rewritten as a to the power y, and then we take that 2 outside. It could have been rewritten in that manner. A to the power 2y can be rewritten as a to the power y and separate those two exponents with the bracket, taking out 2 as an exponent outside those brackets. So similarly, 3 to the power 2 tan of x can be rewritten as 3 to the power tan of x all to the power 2, right? So that is how we will deal uh, with the first term. So let us write it down. It will be 3 to the power tan of x all to the power 2 minus 3 to the power tan of x times 3 equal to 54. Yes. So now you see that actually, as much as you have uh, 3 to the power tan x and 3 to the power tan x, taking out a common factor here won't really help us much. Why? Because in the first term, we don't just have 3 to the power tan x. We have what? 3 to the power tan x all squared. So we have two of those multiplying one another. So a common factor won't help us really that much. But there is something that will help us. And what is that? We can say let k to be equal to 3 to the power tan x, the k method. Remember about it in algebra. So in the place of 3 to the power tan x, we will say now k, which will be k squared, minus, in the place of 3 to the power tan x, we will say k times 3, all equal to 54. Then let us just rearrange. K to the power 2 minus 3k minus 54, all equal to 0. So I've just taken the 54 from the right-hand side to the left-hand side of the equation. And then what do we have here? We have that A is equal to 1, B is equal to minus 3, and C is equal to minus 54. Therefore, we can use our quadratic formula to calculate for the value of K. What is the value of K? K, therefore, is equal to minus B plus or minus the square root of B squared minus 4AC, all divided by 2A. Right. Then we substitute within that quadratic formula. B will be minus 3. In the place of B squared, we substitute by minus 3 all squared. In the place of A, we substitute by 1. In the place of C, we substitute by minus 54. And we say all divided by 2A. What is A? 1. And then when we press our calculator, we will discover that actually K is equal to 9, or K is equal to minus 6. But we are not solving for K here. Remember, what is K? K is 3 to the power tan x. So that will be in the place of K now, we substitute by 3 to the power tan of x. This is equal to 9. But what is 9 in terms of 3? That will be 3 to the power 2. Remember the law of exponent that we spoke about. When the bases are the same, we then equate the exponents. So tan of x is then equal to 2. Why? Because when the bases are the same, we then equate the exponents. Right. Then we come to this side. In the place of k, we substitute by 3 to the power tan x. all of that being equal to -6. And that has no solution because of this negative. It has no solution. So therefore, the only equation that we will continue with is tan of x equal to -2. And that, folks, is how we fight for that tan to be the subject of the equation. What do we apply? The laws of exponents. Most of what we did here is not trigonometry. It is algebra. So if you find yourself struggling a bit with what is happening here, your issue is not trigonometry, it is algebra. Right. Let us go to our third step, which is to do what? To select quadrants. To select quadrants. We see that the equation that we are working with is, which is tan of x equal to 2. This constant is 2, which is positive, which means also tan is positive in the first and in the third quadrant. So those are the quadrants that we will be working with. Then let us define or determine our reference angle. This shouldn't be a struggle for you at this time. Determining the reference angle, choosing quadrants, and it shouldn't be an issue. All right, then we will say inverse of tan, substitute 2, then our reference angle will therefore be equal to 63.43 degrees. Right, then we go to our very last step, which is also something that you shouldn't really be struggling with, especially if you have been following ever since the beginning of this episode. So the problem that we are solving here is tan x equal to 2, where the reference angle is equal to 63 degrees, 63.4 degrees. We selected the first quadrant where our reduction formula is just theta. Then we will say x is equal to theta, which is theta, the reference angle, 63.43 degrees plus k times 180 degrees. Why? Because we're dealing with tan. Or which other quadrant? It would be the third quadrant, which is, in the third quadrant, we have 180 degrees plus theta, where theta is our reference angle. Then our answer is x equal to 180 degrees plus theta, which is 63.43 degrees plus k times 118 degrees. Then that would be x is equal to 243 degrees, 43 degrees plus k times 118 degrees. 243 degrees. 243, degrees. Then k is the element of integers. And folks, that is how we solve this problem. All right, I think the only thing new for you might be step 2, the use of those laws of exponents, and that is not trigonometry, rather algebra. All right, and that, folks, is the end of this episode. I've enjoyed myself, and I really, really hope and pray that you also enjoyed yourself.
And it's a wrap, Buffet 2. Thank you for tuning in. We hope this tutorial brought you one step closer to becoming a star. If you want more, let us match you with one of our patient and passionate facilitators who will walk you through the principles and concepts at your own pace. You can also sign up for our termly virtual revision initiative, designed to sharpen your problem-solving skills and boost your confidence for school examinations. All our contact details are in the description below. And hey, they say good people shall share, so as a good person, kindly share this with your community. Lastly, kindly like, subscribe, and comment below to let us know what you'd like us to cover next. Keep improving, keep becoming a star. The journey continues with basics to brilliancy, mastering the basics and mastering the art of problem solving.